Welcome to the video lecture on properties of trigonometric functions. Let's recall that on a unit circle, if we have an angle theta that is in standard position, then its initial side is on the positive x-axis, and that angle theta sweeps up to some point on the edge of our circle with coordinates p, x, y. This point x, y is called your terminal point, and if this is a unit circle with a radius of 1, then this angle theta also matches this arc length over here, which sometimes we call t or s. So if we have this setup going on, then what we've defined is the sine of theta is defined to be the y-coordinate of this terminal point. The cosine of theta is defined to be the x-coordinate of our terminal point. Tangent of theta is defined to be y over x, where x cannot equal to 0. Cosecant of theta is the reciprocal of sine, so it's 1 over y, assuming that y does not equal 0. Secant of theta is 1 over x, assuming x is not 0, so secant is the reciprocal of cosine. And cotangent of theta is x over y, that's assuming y is not 0, and that makes cotangent the reciprocal of tangent. Now think for a moment here where some of these values might become 0. Where on a unit circle does the x value hit 0? Well, that's going to be up here at the top of the circle or down here at the bottom of the circle. And in terms of radians, this angle theta could either be x equals to 0 at a theta of either pi over 2 or 90 degrees up here at the top, or 3 pi over 2 down at the bottom, or any multiple of 2 pi of those, adding 2 pi's or subtracting 2 pi's. How about when y would equal to 0? So what would make this cotangent, for example, undefined? When does y hit 0? Well, y is going to be 0 over here, which is at 0 for theta, or over here on this side, which is a theta of pi, or 180 degrees, or back to 2 pi, or any integer multiple of pi. So 1 pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi, and so on. So x hits 0 at all these odd multiples of pi over 2, and y equals to 0 at all the integer multiples of pi. We'll come back to that in a little while. Now these definitions up here assume that you are on a unit circle, but the same definitions apply even if you're not on a unit circle. So suppose that we're on a circle of radius r, where p is the terminal point on that circle. So this time we would be talking about a picture that looks like this, and we still have this angle theta, and we still have this terminal point, but this time our radius is r. And if you imagine dropping this perpendicular down, what we're looking at is a little right triangle where the horizontal leg is x, the vertical leg is y, and this time the hypotenuse is r. So if your circle is not a unit circle and your radius is not 1, you can still define sine of theta, but this time sine of theta is not just y, it would be y over r. And cosine of theta would be x over r. Tangent of theta would still be y over x. Cosecant of theta would be the reciprocal of the sine, so this time it would be r over y. Secant of theta would be r over x, and cotangent of theta would be x over y. So the definition extends to other circles with other radii. Okay? Now since sine and theta are referring to the x and y coordinates on our circle, and theta can be any angle, I can go as big or as small as I want, it follows that the domain of the sine and cosine functions can be all real numbers. So you're allowed to let theta here be any angle at all for sine and cosine, and it'll still be defined. So let's make a list of our domains and ranges for all of our 6 trigonometric functions. And refer to that unit circle again, because on that unit circle, it's this terminal point with coordinates x, y that are determining all of these trig functions. So since theta can be any angle whatsoever, the domain of the sine function can be all real numbers. And that's also true for cosine as well. Unfortunately, though, tangent of theta, cotangent of theta, secant and cosecant have restricted domains, and that goes back to this issue up here, where tangent is defined to be a fraction, y over x. So where might this become undefined? It's going to become undefined whenever x might be 0. And that was all of those odd multiples of pi over 2. So one way that I could write that for tangent is that it is all reals except odd integer multiples of pi over 2, and sometimes you see this written as 2k plus 1 times pi over 2, because 2k plus 1 generates every odd number if you let k be any integer. So for example, if k was 0, then this would be 1. If k was 1, then this would be 3. If k was 2, then this would be 5. So we're generating all of the odds by this expression 2k plus 1. And if k is negative, then you get all those negative odd numbers. So if k was negative 1, this would be negative 1. If k was negative 2, then this would be negative 3, and so forth. So this fancy expression right here is just a way of generalizing all of those odd integer multiples of pi over 2. So let's go back to our definition of tangent of theta. It had an x in the denominator, so that's why we didn't want that x to be any of those odd integer multiples. If you look at the other three functions down here, secant of theta, which is the reciprocal of cosine, also has an x in the denominator. So we would not want that to become undefined either. So secant of theta is going to have the same domain as tangent of theta because they both have x's in your denominator. So I am going to copy down for the domain of secant the same thing that I had for tangent. So this will be all reals except the odd integer multiples of pi over 2. Or in other words, everything except things of the form 2k plus 1 times pi over 2. Now let's look at the domain of cotangent and cosecant of theta. Cotangent has a y in the denominator, and so does cosecant of theta. So where might these fractions become undefined? That would happen whenever y was 0. And we said that y hits 0 at 0, pi, 2 pi, 3 pi, and all the negatives of those as well. So all the integer multiples of pi. So let's see how we could write that out. So in words, the domain of cotangent would be all reals except integer multiples of pi. And a fancy way of writing that would be all real numbers except for k pi, where k here is an integer. So if k is 0, then this is 0. If k is 1, then this is pi. If k is 2, then this is 2 pi. If k is negative 1, then it's negative pi, and so on. So we're generating all of those integer multiples of pi that we wanted to leave out. And cosecant of theta was also dividing by y, so its domain would be the same as cotangent. So all reals except integer multiples of pi. So all reals except for things of the form k pi, where k is that integer. Okay? Now to get the ranges, sometimes it's more useful to look at a graph, but we haven't talked about how to graph these functions yet, so we're just going to try and figure out what the range of these functions are based on this unit circle. So think about our unit circle here. The radius is 1 in each direction, and the sign is the y value. So what kind of y values will these points have if it's lying on the unit circle? What's the smallest y value that it goes through? Negative 1 down here. And what's the biggest y value that it goes through? Positive 1 up here. So the range of sign would be negative 1 up to positive 1. Similarly for cosine, the smallest x that the circle goes through is -1, and the largest x is +1. So the range of cosine is also -1 to +1. Now for the tangent. The tangent, remember, is defined to be y over x. So if we think about that, that definitely is going to hit 0 because y does hit 0 on this unit circle. And if x goes to 0, then we would be dividing in this fraction by something really, really small. And if you think about dividing a fraction by something really, really small, that makes the fraction get really, really big. So as x goes to 0, this fraction is going to blow up and go to either positive infinity or negative infinity, depending on whether x is positive or negative. So what this implies is that we are hitting all possible values from -infinity up to positive infinity. So the range of tangent is -infinity to positive infinity. And for the same argument, the range of cotangent, which is defined to be x over y, would also be all reals. And you'll see this more clearly when we talk about the graphs of tangent and cotangent as well. Whoops. Alright, now let's talk about the range of secant and cosecant. Secant is defined to be 1 over x. So let's think about what the largest x value that this could take on. The largest x would be 1 on that unit circle. So if x is 1 in the bottom, then 1 over x goes to 1. And when x is the largest, that makes this fraction its smallest. So this is going to get as small as 1. What happens if x goes to 0? Then the fraction 1 over something really small gets really, really big. So what that means is that in the positive x's anyway, the smallest that secant of theta will ever take on is 1, and then as x gets really close to 0, this fraction will blow up to infinity. And the same thing happens in the negative direction, but we would go from -infinity up to -1. So you get a range that's between -infinity and -1, and 1 up to positive infinity. The range of cosecant is exactly the same. So the largest that y could be would be 1, so the smallest this fraction would be is also 1. And as y goes to 0, this fraction blows up. And in the negative direction, the biggest that y could be would be -1, which makes the fraction -1, and as y goes to 0 through the negatives, this is going to blow up towards -infinity. So the range of secant and cosecant are the same. Okay? The next property of trigonometric functions that we're going to talk about is the fact that they're all periodic. So let's kind of explore what that means. If you think about a unit circle and an angle theta, which hits at a terminal point P with coordinates x, y, then we know that the sine of theta is equal to the y coordinate. So what would happen if we looked at the sine of theta plus 2 pi? Well, that angle would be this angle theta plus a full revolution going around. So if we go all the way around 2 pi plus our theta, look at where it lands us. It lands us right at the same terminal point P, and therefore the y coordinate is going to represent the sine of that angle. So sine of theta plus 2 pi is also equal to y. And this would also apply if you were talking about the cosine function as well. Cosine of theta would be the x value, and if I go cosine of theta plus 2 pi, I would also equal to x as well. Now what happens if we went sine of theta plus 4 pi, or 6 pi, or 8 pi? Or if we went sine of theta minus 2 pi or minus 4 pi, that's still going to land us at the same terminal point P every time, and therefore the y coordinate is always going to be the same. And those sine values for all of those multiples of 2 pi are going to be the same as well. So the way that we would write that is sine of theta plus
2 pi k is always equal to y in this case. And this k just represents any integer value, whether that's positive or negative. So theta plus 2 pi k represents all the integer multiples of theta. So that tells us that the period of the sine function is 2 pi. If we take any angle plus a multiple of 2 pi, we're going to get back the same value. That's what periodicity means. It repeats the same values with a frequency of 2 pi. So it turns out that the sine function, as well as the cosine function, as well as their reciprocals, secant and cosecant, all have a period of 2 pi. That means for angles that are adding multiples of 2 pi, you're going to get back the same value. Now, tangent and cotangent repeat more often. They relapse in quadrants 1 and 3 or quadrants 2 and 4. So they have a shorter period of just pi. So another way to write those periodic properties would be to write them in these statements right here. So sine of theta plus 2 pi gets you back to sine. Cosine of theta plus 2 pi gets you back to cosine. Tangent of theta plus pi gets you back to tangent. Cotangent of theta plus pi will have the same value as cotangent of theta. And then secant and cosecant of theta plus 2 pi gets you back to secant of theta or cosecant of theta. So I would strongly recommend that you memorize this statement right here, that the period of sine, cosine, and its reciprocals, secant and cosecant, is always 2 pi, and the period of tangent and its reciprocal cotangent is always pi.
Okay, let's take a look now at the signs of our trigonometric functions in the various quadrants. So in this diagram right here, I just have written down all of the different possible signs for our x and our y coordinates of our terminal points. So for example, in quadrant 1, which is right here, both x and y are positive. In quadrant 2, just the x is negative. In quadrant 3, both are negative. And in quadrant 4, just the y is negative. So you have to remember how all of these are defined. X is cosine. So x would be positive in quadrant 1, so that makes cosine positive in quadrant 1. X is also positive in quadrant 4, so that would make cosine positive in quadrant 4 as well. And since the reciprocal of cosine would be secant, then so would secant of theta have to be positive in those two quadrants as well. In quadrant 2, x is negative. In quadrant 3, x is negative. So in those two quadrants, cosine would have to be, negative, and so would its reciprocal secant. If we look at the y coordinates here, y is the sine value. So the y value is positive in quadrants 1 and 2, so that means the sine has to be positive in quadrants 1 and 2. So sine would be positive in quadrant 1 and in quadrant 2, and its reciprocal is cosecant of theta, so its reciprocal would also be positive in those two quadrants. Y is negative in quadrant 3 and 4, so sine would be negative in quadrant 3, and sine would be negative in quadrant 4, and so would its reciprocal. Oops. And then finally, if we look at tangent, tangent is y over x. So if you divide a positive y by a positive x, it's going to stay positive. So tangent is positive in quadrant 1, and so would its reciprocal be cotangent. In quadrant 2, if you take a positive y divided by a negative x, it's going to stay negative. So tangent is negative in quadrant 2, so would its reciprocal. In quadrant 3, a negative divided by a negative becomes positive, so in quadrant 3, tangent and cotangent are both positive. And in quadrant 4, a negative divided by a positive stays negative. So here is where we have positives. Everything is positive in quadrant 1, nothing is negative in quadrant 1. In quadrant 2, sine and cosecant are positive, the rest are negative. In quadrant 3, tangent and cotangent are positive, the rest are negative. And in quadrant 4, cosine and secant are positive, the rest are negative. Now to kind of help you remember that, there is a little saying that you can remember. In quadrant 1, all of them are positive. In quadrant 2, it was just the sine and its reciprocal cosecant. In quadrant 3, it was just tangent that was positive and its reciprocal cotangent. And in quadrant 4, it was just the cosine and its reciprocal secant. So if you use the acronym all sine, tangent, and cosine and use that A, that S, that T, and that C, you can try to remember that by thinking all students take calculus. So the A stands for all, quadrant 1. The S stands for sine functions in quadrant 2, being positive. The T stands for tangent, being positive in quadrant 3. And the C stands for cosines, being positive in quadrant 4. Okay, more properties. So let's talk about whether or not our trig functions are even or odd. So let's take a look at this picture. We have our unit circle again. We have our angle theta. I'm also going to consider negative theta, which is the same angle amount but just going in the clockwise direction, so going down, and the corresponding terminal points. So if these are truly the same measure of angle, then if this terminal point is x comma y, by symmetry, this terminal point would also have the same x coordinate because we're still on the positive side of the x-axis, but the y-coordinate would just be opposite in sign. So let's take a look then at what happens if we consider sine of negative theta. If we take a look at sine of negative theta, that would put us at this terminal point right here, and the sine of that angle is supposed to be its y-coordinate, which in this case is minus y. But y is by definition the sine of positive theta, but we still have that negative pulled out, so we can think of sine of negative theta as minus sine of theta, and that's the definition of being odd. Remember that something is odd if f of negative x gives you back minus f of positive x. So this is the definition of being odd, so sine must be an odd function. If we take a look at cosine of minus theta, cosine of minus theta would be the x-coordinate of this terminal point, which is just x. And x up here corresponds to the cosine of positive theta. So we showed that cosine of minus theta is exactly the same thing as cosine of positive theta, and that's the definition of being even, if f of minus x equals f of positive x. So that shows, that's a proof that cosine is an even function. Now let's look at tangent. So if we wanted the tangent of minus theta, that would be using this terminal point down here. We would want to take its y-coordinate, which is negative y, divided by its x-coordinate, which is x. And if I pull that minus out front and think of this as minus the quantity y over x is this y over this x, so that would be the tangent of positive theta. So I'm going to replace this with tangent of theta and leave that minus out front. So tangent of minus theta gives me back minus tangent of theta. So it's kind of like we're able to pull that negative out front of our function. And when we're able to do that, that implies that we're talking about an odd function. So the reciprocal functions would be exactly the same as their pair. So sine of negative theta we showed was minus sine of theta. So its reciprocal would also do the same thing. We can pull that negative out, and we would just get negative cosecant of theta. And that shows that, that these two functions are odd. For cosine, we were able to just lose that negative altogether. Cosine of minus theta gave us back cosine of positive theta. So its reciprocal function would do the same, would act the same way. So secant of minus theta would be secant of positive theta, and that's, I keep writing these backwards, that would show that these two functions are by definition even. And then finally, for tangent of negative theta, again, we were able to pull that negative out front of the tangent. And so its reciprocal would act the same way, so negative cotangent of theta, and that's the definition of them being odd. So every trig function is odd except cosine and secant. Now the next set of things that we're going to look at are called the reciprocal identities, and we've already talked about these quite a bit, but you do want to have these memorized. We know that cosecant of theta is the reciprocal of sine, so sometimes we write that as 1 over sine of theta. Secant is the reciprocal of cosine, so that's the same as 1 over cosine. Cotangent of theta is the reciprocal of tangent, so 1 over tangent. Tangent of theta, normally we think of that as being y over x, but y is sine and x is cosine. So you can think of tangent of theta as being the sine function divided by the cosine function. Therefore, its reciprocal, which is cotangent, would have to be the cosine over the sine. So you want to have these 5 reciprocal identities memorized. Next, we are talking about what we call the Pythagorean identities, and these 3 identities are very, very important, especially when we start talking about identities and trigonometric functions. So you will use these quite often, so you definitely want to have these memorized. And we're going to prove each of these. So the first one says that sine squared theta plus cosine squared theta has to equal 1. And why does that have to be true? Well, remember that sine of theta is defined to be y, and we're squaring sine, so we would square the y. Cosine of theta is defined to be x, and we're squaring it. Why does y squared plus x squared have to equal to 1? It has to because we're on a unit circle, and that's the equation of our unit circle. So this is true. Okay, so it's a very basic proof. It's just true because we are on a unit circle. Okay, now if we can take this first Pythagorean identity as true, we're going to use it to prove the other ones are true. So let's prove that tangent squared theta plus 1 equals to secant squared theta. So I'm going to start with the fact that we know sine squared theta plus cosine squared theta always equals to 1. We already know that that's true because we're on a unit circle. And what I'm going to do is I'm going to divide everything through by cosine squared theta. As long as you do the same thing to both sides of your equation, you're maintaining equivalency. Now sine squared theta over cosine squared theta is like sine theta over cosine theta, which we just talked about on the last page. That's tangent of theta, and we're squaring it. Cosine squared over cosine squared just becomes 1, and 1 over cosine squared is like 1 over cosine, which we said was the reciprocal, so that's secant, and it's being squared as well. So we've just proven this second Pythagorean identity. So let's do the same thing, the same idea, to prove that 1 plus cotan squared theta equals cosecant squared theta. So we're going to start with our basic Pythagorean identity, sine squared plus cosine squared equals to 1. And this time, instead of dividing every term by cosine squared, I'm going to divide every term by sine squared. And again, I'm doing it to both sides, so it's still equivalent to what I'm starting with. Sine squared over sine squared becomes a 1. Cosine squared over sine squared is like a cosine over a sine, and that's the definition of cotangent, and we're squaring it. And then 1 over sine squared is like a 1 over sine, which is a cosecant, and we're squaring that as well. So again, we've proven that second Pythagorean identity. Now I keep referencing this, and I suppose I should mention that this notation, sine squared theta, really means the quantity sine of theta squared. They're equivalent. But this just gets a little tedious to write with those parentheses every time. So we just write that little square in between sine and theta. So whenever you see the little 2 in between, it means that entire trig function squared. Now the next couple of problems that we're going to do are pretty common types of problems that you'll want to know how to do. This first one says to find the value of all the trigonometric functions if you know that sine of theta is equal to 3/4, and we're told that theta is in quadrant 2. Now there's a couple ways to do this. We want to find all 6 trig functions. So we're looking to find sine of theta, cosine of theta, and tangent of theta, and then the reciprocals, cosecant, secant, and cotangent. Now the only one of these that we know is 3/4 is equal to sine. Because of that, we should also know that the cosecant, the reciprocal, would have to be 4/3. Based on just that, we need to figure out what these other 4 are. So the first way I'm going to show you how to do this is to use a unit circle. So if we have a unit circle, remember that your radius is 1, and what I'm going to do is I'm going to draw a triangle. And we're going to use the fact that this angle is in quadrant 2. So I'm going to draw a little triangle over here in quadrant 2. My angle theta would be right here, and because we're on a unit circle, you want to kind of imagine that circle around like this. That radius of that circle is really that hypotenuse. So we have a terminal point right here, which is an x comma y, and we're told that the sine of theta is 3/4. Now when you're on a unit circle, what does sine of theta correspond to? Sine of theta is the y coordinate of your terminal point. So if sine of theta is 3/4, then the y coordinate of this terminal point should be 3/4 as well. And that y coordinate is this height y right here. So what we get is this little right triangle, this is a right angle right here, where the vertical leg is 3/4, the hypotenuse is 1 because we're on the unit circle, so all we need to do is find out what x is, and x will be the cosine value. Now how do we find x if we know that this is a right triangle? We can just use Pythagorean theorem. We know that x squared plus 3/4 squared has to equal 1 squared. So let's just do a little bit of solving there. We get x squared plus 9/16 equals to 1. If I subtract 9/16, remember that 1 is the same as 16/16. So if I subtract 9/16 over to the other side, 16 minus 9 makes this 7/16. And if I take the square root of both sides, you would get plus or minus square root of 7, and square root of 16 reduces to 4. Now here's where that quadrant is important. We are in quadrant 2, and in quadrant 2, x needs to be negative. So I am going to use the negative answer here. So I'm going to let x, let me just go ahead and erase this, x is negative square root of 7/4. And the x coordinate of this terminal point is cosine. So we now know the value of cosine, and we therefore know its secant value because the secant is just the reciprocal. So if I flip this over, we would get negative 4 over square root of 7. If you want to rationalize, that would be negative 4 root 7 over 7. Then how do we find tangent? Well, tangent by definition is y divided by x. So the y coordinate was that 3/4, and the x coordinate was this negative square root of 7 over 4. The 4's are going to cancel, so we get negative 3 over root 7. Or if you rationalize, negative 3 root 7 over 7. Cotangent is just x over y, or the reciprocal of this fraction that we got for tangent. So if I flip over this fraction, the negative root 7 goes on top and the 3 goes on bottom. So there's our cotangent value. And here's all 6 of our trig values, just from knowing 1. Okay? Now that's one option, using a triangle, drawing a triangle, and assuming that you're on that unit circle and using the Pythagorean theorem to help you find the x and the y coordinates that correspond to the legs of that right triangle. The second option is to use some of those properties, those Pythagorean identities that we already knew. So if I make my list again, we know that sine of theta is 3/4. Therefore, we know cosecant of theta must be 4/3. And we're looking to find cosine of theta and its reciprocal secant, and tangent of theta and its reciprocal cotangent. So to do it this way, and this is totally your option, whichever way you want to do it is up to you, we're going to use those Pythagorean identities. And I'm going to start with that very famous one, sine squared theta plus cosine squared theta always equals to 1 because we're on that unit circle. I know what the sine of theta is. It's 3/4. So I'm going to substitute in 3/4. And remember, sine squared means to take that sine value and square the whole quantity. So what I can do then is solve this equation. So this gives me that 9/16. Subtracting that 9/16 to the other side gives me that 7/16. And if I take the square root of both sides, that's going to give me cosine of theta, and it could either be plus or minus square root of 7/4. Since we are in quadrant 2, cosine of theta is negative in quadrant 2. So I want the minus case only. So minus root 7/4. Therefore, the reciprocal secant would be minus 4/root 7. And then to get tangent, we're going to use that reciprocal identity, which says that tangent is, by definition, sine of theta over cosine of theta. So the sine of theta was 3/4. The cosine of theta we found out to be negative root 7/4. The 4's cancel, and we get that negative 3/root 7. So its reciprocal cotangent would be negative root 7/3. So it's really the same technique because we really are doing the same amount of work solving that Pythagorean theorem essentially, but you can think about it either way, using identities or drawing a right triangle. Let's try another example that's similar to that. Given that tangent of theta is equal to 1/2 and sine of theta is less than 0, find the exact value of each of the remaining 5 trigonometric functions of theta. So let's make our list again. We're going to want sine of theta and its reciprocal cosecant. We're going to want cosine and its reciprocal secant. We want tangent and its reciprocal cotangent. The only one that they're giving me is tangent, equal to 1/2. So right away I know its reciprocal must be 2, so that's what cotangent must equal to. So based on that alone, we want to try to figure out these other 4. Now let's talk a little bit about quadrants for a moment, because quadrants are always very important to determine what signs, positives and negatives, you need to have on these answers. Now notice that tangent of theta is equal to positive 1/2. In which 2 quadrants is tangent going to be positive? Tangent is positive in quadrants 1, where everything is positive, or in quadrant 3, where everything is negative, so that the quotient becomes positive. Where is sine of theta less than 0? In other words, where is sine of theta negative? Well, sine is the y value, and the y values are negative in either quadrant 3 or quadrant 4. So combine those 2 things together. Where is tangent positive, but at the same time sine of theta negative? The only place where these overlap is in quadrant 3. So that means we must be talking about an angle that's in quadrant 3. Okay, so we want to keep that in mind. Now in this method, we're going to draw a triangle just like we did in the last example, but this time we're not going to use a unit circle. We're just going to use a general circle of some radius r. And I'll show you why that's important. If we are told that tangent of theta is equal to 1/2, we also know that by definition tangent of theta is y over x. So a nice simple way to create your triangle is to let the y side be the 1 and the x side be the 2. So let's draw a triangle. Which quadrant do we want to be in? We said we wanted to be in quadrant 3. So I'm going to draw a right triangle over here in quadrant 3. Here's my angle theta, here's my right angle, and this is your x comma y. So this is x, and this is y, and this is my radius r. And based on how tangent of theta was given to us, 1/2, I'm going to let this y value be the 1, and I'm going to let this x value be the 2. So we really have a right triangle with legs 1 and 2. So how could we find out what this hypotenuse needs to be? Use Pythagorean theorem. So the 2 squared plus the 1 squared has to equal the r squared. So we get 4 plus 1 equals r squared, so r squared equals to 5. Therefore, r equals square root of 5. So we're talking about a triangle where the legs are 2, 1, and square root of 5. Now based on that, we're going to figure out what these values are over here. Now remember, when you're not on a unit circle, sine of theta isn't just y. Sine of theta is y over r, y over whatever that hypotenuse or that radius is. So this case, our y was 1 and our x was 2. So I need to take this 1 over this radius square root of 5. So this is going to be 1 over square root of 5. Now let's think about our signs. Remember that we're in quadrant 3, so this x isn't really just 2, it's actually a negative 2, and this y is actually a negative 1. So the coordinates of this point would be negative 2 comma negative 1 because we are in quadrant 3. So I really need to have a negative in front of that 1 on top. Your hypotenuse will always be positive. It's just the two x's and y's that could be positive or negative. So this is good because we know that in quadrant 3 sine is supposed to be a negative value. So we are getting that. We're getting negative 1 over root 5. So what would the reciprocal of that be? If I flip that over, I'm going to keep that negative, but then it just becomes square root of 5. Now cosine, by definition, when we're on a circle that doesn't have a radius of 1, cosine is defined to be x over r. So the x value is this negative 2, and the radius is that square root of 5. And that means its reciprocal would become negative square root of 5 over 2. So all 4 of these trig values were negative, like they're supposed to be in quadrant 3, and tangent and cotangent were positive. So here's my 6 values. So that's option 1, using a triangle again, but this time the triangle didn't have a hypotenuse of 1 because we just let y be the top value of our tangent and we let x be the bottom value of our tangent. And that way we created a new triangle that had sort of this scaled hypotenuse. Let's try the same problem again, but this time we're going to use some identities. So we know what tangent of theta is. We know tangent of theta is 1/2. So if I want to find out sine of theta, cosecant, cosine, secant, tangent we know is 1/2, and cotangent therefore is 2. The only one of these that I really was given was this tangent. So if I'm going to use identities, I want to use an identity that uses tangent. So I'm going to use that Pythagorean identity that says tangent squared theta plus 1 equals secant squared theta. And that way I can plug in 1/2 for this tangent of theta. Now we need to square that. So 1/2 squared becomes 1/4, and 1 is 4/4. So if I get a common denominator there, 1/4 plus 4/4 is 5/4. And to solve for secant theta, I would take the square root of both sides. This could be plus or minus. I'd get square root of 5 over 2 when I reduce. And remember here, we're in quadrant 3, and in quadrant 3, secant is supposed to be negative. So that means secant of theta should be negative root 5 over 2, so its reciprocal would be negative 2 over root 5. Now once we know what secant and cosine are, how are we going to figure out sine and cosecant? Well, there's a couple ways to do that. One option is to use that reciprocal identity that says tangent of theta is by definition sine over cosine. So what I'm going to do is I'm going to substitute in 1/2 for the tangent. I don't know what sine is yet, but we just figured out that cosine is -2 over root 5. So how could I solve this equation for sine of theta? Well, I can multiply by this denominator. So I'm going to multiply both sides by -2 over square root of 5 so that these two fractions cancel out. Likewise, these 2's will cancel out, and what we end up with is -1 over root 5 is what we're left with for sine. So sine is going to be -1 over root 5, so that makes its reciprocal negative square root of 5. So on these problems, and you will definitely see these on quizzes and tests and homework, you can either draw a triangle and think of it that way, or you can use identities. It's totally up to you how you do these. Okay, one last problem. This is something you'll probably see in homework as well. It says express all of our trigonometric functions in terms of the cotangent function. So let's make our list again. We're wanting sine theta and cosecant, cosine theta and secant, tangent theta and cotangent. And this one, it sounds a little bit weird, but what we're trying to do is we're trying to write all 6 of these so that they are on this right-hand side of the equals something in terms of cotangent. Now, cotangent of theta is already in terms of cotangent, so that one we don't need to do anything for. Likewise, we can figure out tangent of theta and write it in terms of cotangent because tangent, remember, is the reciprocal of cotangent. So tangent of theta would be 1 over cotangent theta. So what we're looking to do up here in these 4 spots is come up with some kind of formula like this one is, where the formula uses cotangent theta as kind of your variable. So how could we possibly do that? Well, what we're trying to work with is this cotangent. So I'm going to think in terms of those identities that we have, and the only Pythagorean identity that I have that refers to a cotangent is the one that says 1 plus cotangent squared theta equals cosecant squared theta. So if I solved this for cosecant, then it would be in terms of cotangent. So all I have to do to solve for this cosecant is undo that square. So I'm going to take a square root of both signs, and that would be a plus or minus square root of 1 plus cotangent squared theta equals this cosecant theta. So this is what I mean by writing cosecant theta in terms of a formula that uses cotangent. So we're going to write this right over here. So we've now written cosecant in terms of cotangent. Now if we know cosecant, then we know sine, because we just need to take the reciprocal of this answer, flip it over, and we'll know what sine is. So this is going to be 1 over plus or minus square root of 1 plus cotangent squared theta. Notice that I'm leaving the plus or minus symbols in there because it doesn't tell me anything about what quadrant we're supposed to be in. So these could be pluses or minuses depending on the quadrant. So we've got 4 out of the 6. Now we need to figure out what cosine theta needs to be. So to figure out cosine, I'm going to use another Pythagorean identity, and I'm going to use the one that says sine squared theta plus cosine squared theta equals to 1, because I'm looking to find out what cosine is. Now in order to do that, I need to know what sine of theta is, and we just figured that out. So sine of theta was 1 over plus or minus the square root of 1 plus cotangent squared theta, and that was sine, and we want sine squared, so I want to square all of that. So what happens when we square it? Well, the plus and the minus signs are both going to become plus when you square them. The 1 stays 1, and when I square that square root, I lose it. So I just get 1 over 1 plus cotangent squared. So now what I'm going to do is I'm going to try to isolate this cosine squared so I can solve for it. So I'm going to subtract this entire fraction over to the other side. So we get cosine squared theta equals 1 minus this fraction. Now this is kind of messy, so what I'm going to do next here is get a common denominator. And my only denominator is that 1 plus cotangent squared. The numerator on this fraction stays 1. We want this fraction to be equivalent to this 1 right here. So I need the numerator to be exactly the same as the denominator so that this is really just a fancy version of 1. But now that we have common denominators, I can consolidate these two fractions with one single fraction, and 1 plus cotangent squared theta minus 1 makes these 1's cancel out. And we're just left with a cotangent squared theta on top. And we're almost done. We have this cosine isolated, but we need to undo the square. So I'm going to take the square root of both sides. We're going to get that plus or minus symbol. And we have this nice perfect square on top, so that can reduce to just a cotangent theta. But I can't reduce the bottom because it's a sum. So you need to leave that square root around that whole sum. So there's what cosine equals to in terms of cotangent theta. So we're going to write that up here. So cosine is plus or minus cotangent theta over this big square root. And if we know cosine, we know secant. We just have to flip it over. So we get that big square root on the top, and we get the cotangent of theta on the bottom. So each one of our 6 functions are written in terms of cotangent theta. So these would be my answers. Alright, we talked about a lot of properties today and several things that you need to have memorized. So make sure you practice those reciprocal identities and those Pythagorean identities. Know about even and odd, and just know your basic definitions of what sine, cosine, tangent are equal to in terms of y's and x's, etc. Know your domains and ranges, and know where all 6 trig functions are positive and negative. Good luck! That concludes our lecture on properties of trigonometric functions.